Bismillah ar-Rahman ar-Rahim. We'll be discussing work, energy, and power. We consider work as energy. So this importance will be referred to especially to the ventilation, the cardiac output. You see, work is a source of energy. You see, as we know before, that force is the power that gives an object of 1 kilogram an acceleration of 1 meter per second. You see, this is the force in which its unit is Newton. Suppose this force in the direction of this force moved the subject for only 1 meter. So at that time, we can say that it created 1 joule. So the work done created an energy of 1 joule. This is the definition of 1 joule. Of course, we know that the force of gravity on 102 gram of whatever subject is 1 Newton. So as you can see from the figure, Newton carrying an apple with the same weight as we mentioned before, which is 1 Newton, and I elevated only for 1 meter. As long as I elevated it for 1 meter, thus I created 1 joule energy. I made a work that gave 1 joule energy. Okay, this energy is being stored upwards, and then whenever I leave it, it is transferred to a potential energy. So the mechanical energy is transferred to a mechanical potential energy. So that work done equals pressure per distance. Of course, the importance, as we said, will be referred to ventilation and cardiac output or the circulation. This figure represents a constant pressure ventilator, means that it gives a constant pressure over the process of inspiration. Of course, that does not occur much in ventilators, but it is an example to show off the correlation between the distance and the force. So we have, as we see from the ventilator, we have a mass which creates the force, and then we have is A, which is the surface area, and we have the D, which is the distance of the descent of the pillows, and then we have the pressure created, and then we have a graph on the other side representing inspiration, which is in a constant pressure manner. You see, the volume created during the process of inflation or inspiration is around ½ liter, creating a pressure of 0.6 kilopascal. So by knowing that pressure means force on the surface area, so that force will be the multiplication of both. On the other hand, the volume of this concertina, or we can consider a cylinder, equals the distance of the descent plus the surface area. We'll get a figure as we see that the distance will be over V over A, and then when you combine these two equations, we reach that the end result that the work equals pressure times volume. You see, this is always the work of whether inspiration or expiration, and the work done also by the heart rate, and all will discuss it. Of course, as you see from the graph, the correlation between pressure and volume, it is a rectangular area. You see, showing that the 0.6 kilopascal, when I multiply it by 10, it gives me the figure in centimeter water. You see. So whenever I want to calculate the work, I'm going to multiply these two figures, the pressure and the volume, but we must put in our consideration that it is a Pascal times cubic meter. So we are transferring. Once we are multiplying by the time of 3, and the other is multiplying by the time of -3. To reach to the final conclusion or result that the work of breathing is around 300 millijoule. A figure you must memorize. Most of the ventilators are built up of pressure. They work by increasing the pressure, not constant, all over a procedure. This is a figure of the normal ventilator graft during inspiration and expiration. You can see that it is not constant, the correlation between pressure and volume. Of course, most of the talking about this subject is physiological. You see, the resistance of respiration depends upon the elasticity of the lung and the elasticity of the chest wall, and also affected by the resistance of the movement of the airway and the patency of the airway. All this will create a resistance. We are trying to show a controlled ventilator, what happens in a controlled ventilator. So we're represented by, as we see on the left side, is the ventilator attached to a syringe, which is made of a barrel and a plunger. The plunger is the part that moves through this barrel, and this plunger is attached to a spring representing the resistance of the tissue, you see, and then this plunger is represented by the diaphragm, and as you see, the pressure of the ventilator, which is created by the pillars of the ventilator to reach a figure required, and then on the other side, the pressure manometer gives a hint of the pressure of the lung, as if it is the lung, you see. So this creates, and of course, as we see, a resistance which represents the airway resistance. This it is a sample. Whenever the ventilator, of course, descends, it will expand the plunger, making a stretch or overcoming the stretch of the first of all the spring, or this, I'm sorry, this elastic element was not extended, so that the pressure was zero. And then whenever I expand this by the movement of the plunger, the pressure will increase, created, or it is being shown by the pressure PL. This is the graph representing what happens by constant pressure ventilator. We can see that it creates a rectangular figure, and we can see that the pressure has been increased to reach 0.6, and the volume is increased to half a liter. And of course, during the half of the period, we are often coming the resistance of the elastic tissue of the lung and the chest wall, and then after the second half of this curve represents, of course, overcoming the resistance of the airway. Also, this is a graph showing the relation between the pressure and the volume in the example we shown before. The work of expiration mostly is from the stored injury during the process of inspiration. Of course, to overcome, of course, you must overcome the resistance of the airway during expiration. Suppose there is some sort of resistance. On the other side, if we represent this correlation in spontaneous ventilation, you can see that the curve will be different. It will not be rectangular. And in that time, I can create another scenario by putting two plungers. You can see two plungers. In between the two plungers is a space we considered as the serious intrapleural pressure. This pressure changes, of course, it can be recorded by the lower esophageal balloon, so that if I want to know that pressure changes, I can notice it by the ballooning of the lower esophagus. And you can see the similar way, but we have this example, we have two plungers moving in the parallel. One of them is representing the diaphragm, and the other one is representing the tissue resistance. And as we can see also the band which is representing the elasticity of the tissue. Of course, all this injury, as a general knowledge, nothing more, is attempt from the ATP. What happens that the oxygen is combined by the electron ZAG in Clark's electrode whenever I wanted to represent it, and creating energy. How can we measure the energy of work of respiration? Of course, we have volume and pressure. Pressure can be measured by the lower esophagus, as we said, and volume we can use the pneumotachograph, as we mentioned before. We don't want to go on further physiological knowledge. There is much knowledge in this subject. The power of breathing, of course, we said before that energy is a work. Work creates an energy, see, and we stated its definition. Power is the rate of energy expansion, the rate. You see, watt, as we all know, equals joule per second. It is the rate. So that if I want to know the power of respiration, knowing that the respiratory rate is around 16, I divide 16 by 20 to correlate it to the second, and I multiply the work of breathing in joule times 16 over 60 will reach around 80 milliwatt. Of course, we always remember that the heat capacity or the heat of the human being is around 80 watt. So this it represent only around figure it out. The respiratory muscles are only 10% efficient to produce the mechanical energy. You see, so the rest of energy is dissipated as heat loss. So actually speaking, the amount of work done by a proper muscle activity without loss of heat will be 10 times. So it will reach around 80, or I'm sorry, it would reach around 800 millivolt. This is actually if it is not lost in heat. So we have 80 of the human being, and we have 800 millivolt, and of course we will not forget that the work of inspiration is around 300 millijoule. Of course, the effect of type of flow will affect the work, and will affect, of course, on the other hand, affect the power. You see, so energy, as we said before, it is the time of pressure, time, volume. On the other hand, the power, which we represented by E, on top of it is a dot, means rate, equals pressure, time, also volume on a dot above, which is rate. As we know that the pressure in the normal laminar flow is proportional to the flow, as we can know that from the graph, it goes straight line, the slope is straight line. On the other hand, the turbulent flow, it is inclined. So the pressure is correlated or proportional to the square of the flow. This difference between the laminar and the turbulent flow will affect, of course, the final assessment of the power. You see, of course, hyperventilation, I'm increasing the rate, so it will increase the amount of work doing, and also on the other hand will affect the power. Of course, pharmacological induced hyperventilation will increase also the work of breathing, and will increase the oxygen requirement, and hence we can reach to final respiratory failure. Time constant means as a general law, it is the compliance. The compliance, as you know, the change of volume to the change of rate, delta V على delta over delta P times resistance will give me the time constant. Time constant, I think the time required for the alveoli to be expanded to a special percent. On the other hand, the work of the heart, especially the left ventricle, of course, the left ventricle is creating, it has, of course, a volume per time. So we have, we multiply the pressure created time, time the volume. So we have 16, which is the pressure, 16 kilopascal, time, the volume, the stroke volume, and then we can shift them. Of course, you must put both figures in a Pascal and cubic meter to reach the final work of the heart, which is around 1,000 millijoule, or in other words, it's 1 joule. So we have the respiration 300 millijoule, and we have the heart almost 1 joule. Of course, measurement of the cardiac output, that we must know the volume and the pressure. The pressure can be gained by cardiac catheters, and the volume can be assessed by ultrasonographic flow measurement or the SINA angiography. Those are 2 methods to measure the volume. Of course, on the other hand, the power of the heart will be, as you can see, the energy to with a dot up above times equals pressure time the V on the top above to reach the power. The end result, the power of the heart is around 1 watt. This is the left ventricle power. Left ventricle power. Of course, the right heart, of course, we can assess all of also the power of the heart by notifying the pulmonary pressure and the volume ejected by the left ventricle, right ventricle, I'm sorry, and we'll reach to the final of 0.2 watts. So they have the left one, and this is the 0.2. So the end result will be 1.2. Also, we can see that is the efficiency of heart is only 15% of this instance. The total of it will reach, instead of 1.2, it must be 8 watt, which represented 10% of the total basal metabolic rate of the human being, which is 80 watt. The blood pressure, of course, and the cardiac output, whenever they are increased, it would make a load on the heart, will increase the work of the heart, and it will increase the power of the heart. I hope I succeeded in what I am doing, and I'm promising to improve my efforts later on. So that's the important thing is to know the definition of work, or at the same time is energy, the definition of power, how much is the power or the work of the heart, and the ventilation. This is the most important, and you must know, of course, all this definition I mentioned before. Wassalamu alaikum wa rahmatullah wa barakatuh.